MapReduce and Distributed Filesystems. MapReduce is a bit like Unix tools, but distributed across potentially thousands of machines. Like Unix tools, it is a fairly blunt, brute force but surprisingly effective tool. A single MapReduce job is comparable to a single Unix process. It takes one or more inputs and produces one or more outputs. As with most Unix tools, running a MapReduce job normally does not modify the input and does not have any side effect other than producing the output. The output Roman 4. One difference is that with HDFS, computing tasks can be scheduled to run on the machine that stores a copy of a particular file, whereas object stores usually keep storage and computation separate. Reading from a local disk has a performance advantage if network bandwidth is a bottleneck. Note, however, that if erasure coding is used, the locality advantage is lost, because the data from several machines must be combined in order to reconstitute the original file. Files are written once, in a sequential fashion, not modifying any existing part of a file once it has been written. While Unix tools use stdin and stdout as input and output, MapReduce jobs read and write files on a distributed file system. In Hadoop's implementation of MapReduce, that file system is called HDFS Hadoop Distributed File System, an open-source re-implementation of the Google File System GFS. Various other distributed file systems besides HDFS exist, such as ClusterFS and the Quantcast File System QFS. Object storage services such as Amazon S3, Azure Blob Storage, and OpenStack Swift are similar in many ways. Roman 4. In this chapter we will mostly use HDFS as a running example, but the principles apply to any distributed file system. HDFS is based on the shared nothing principle. See the introduction to part Roman 2, in contrast to the shared disk approach of network-attached storage NAS and storage area network SAN architectures. Shared disk storage is implemented by a centralized storage appliance, often using custom hardware and special network infrastructure such as fiber channel. On the other hand, the shared nothing approach requires no special hardware, only computers connected by a conventional data center network. HDFS consists of a daemon process running on each machine, exposing a network service that allows other nodes to access files stored on that machine, assuming that every general-purpose machine in a data center has some disks attached to it. A central server called the name node keeps track of which file blocks are stored on which machine. Thus, HDFS conceptually creates one big file system that can use the space on the disks of all machines running the daemon. In order to tolerate machine and disk failures, file blocks are replicated on multiple machines. Replication may mean simply several copies of the same data on multiple machines, as in Chapter 5, or an erasure coding scheme such as Reed-Solomon codes, which allows lost data to be recovered with lower storage overhead than full replication. The techniques are similar to RAID, which provides redundancy across several disks attached to the same machine. The difference is that in a distributed file system, file access and replication are done over a conventional data center network without special hardware. HDFS has scaled well. At the time of writing, the biggest HDFS deployments run on tens of thousands of machines, with combined storage capacity of hundreds of petabytes. Such large scale has become viable because the cost of data storage and access on HDFS, using commodity hardware and open-source software, is much lower than that of the equivalent capacity on a dedicated storage appliance. MapReduce Job Execution. MapReduce is a programming framework with which you can write code to process large datasets in a distributed file system like HDFS. The easiest way of understanding it is by referring back to the web server log analysis example and simple log analysis on page 391. The pattern of data processing in MapReduce is very similar to this example. Read a set of input files and break it up into records. In the web server log example, each record is one line in the log, that is, \n is the record separator. Call the mapper function to extract a key and value from each input record. In the preceding example, the mapper function is awkprint $7. It extracts the URL $7 as the key and leaves the value empty. Sort all of the key value pairs by key. In the log example, this is done by the first sort command. Call the reducer function to iterate over the sorted key value pairs. If there are multiple occurrences of the same key, the sorting has made them adjacent in the list, so it is easy to combine those values without having to keep a lot of state in memory. In the preceding example, the reducer is implemented by the command Unix C, which counts the number of adjacent records with the same key. Those 4 steps can be performed by one MapReduce job. Steps 2 map and 4 reduce are where you write your custom data processing code. Step 1 breaking files into records is handled by the input format parser. Step 3, the sort step, is implicit in MapReduce. You don't have to write it, because the output from the mapper is always sorted before it is given to the reducer. To create a MapReduce job, you need to implement 2 callback functions, the mapper and reducer, which behave as follows. See also MapReduce querying on page. :mapper. The mapper is called once for every input record, and its job is to extract the key and value from the input record. For each input, it may generate any number of key value pairs including none. It does not keep any state from one input record to the next, so each record is handled independently. Reducer. The MapReduce framework takes the key value pairs produced by the mappers, collects all the values belonging to the same key, and calls the reducer with an iterator over that collection of values. The reducer can produce output records such as the number of occurrences of the same URL. In the web server log example, we had a second sort command in step 5, which ranked URLs by number of requests. In MapReduce, if you need a second sorting stage, you can implement it by writing a second MapReduce job and using the output of the first job as input to the second job. Viewed like this, the role of the mapper is to prepare the data by putting it into a form that is suitable for sorting, and the role of the reducer is to process the data that has been sorted. The main difference from pipelines of Unix commands is that MapReduce can parallelize a computation across many machines without you having to write code to explicitly handle the parallelism. The mapper and reducer only operate on one record at a time. They don't need to know where their input is coming from or their output is going to, so the framework can handle the complexities of moving data between machines. It is possible to use standard Unix tools as mappers and reducers in a distributed computation, but more commonly they are implemented as functions in a conventional programming language. In Hadoop MapReduce, the mapper and reducer are each a Java class that implements a particular interface. In MongoDB and CouchDB, mappers and reducers are JavaScript functions. See MapReduce querying on page. Each input file is typically hundreds of megabytes in size. The MapReduce scheduler not shown in the diagram tries to run each mapper on one of the machines that stores a replica of the input file, provided that machine has enough spare RAM and CPU resources to run the map task. This principle is known as putting the computation near the data. It saves copying the input file over the network, reducing network load and increasing locality. Figure 10-1. A MapReduce job with 3 mappers and 3 reducers. In most cases, the application code that should run in the map task is not yet present on the machine that is assigned the task of running it, so the MapReduce framework first copies the code, e.g., JAR files in the case of a Java program, to the appropriate machines. It then starts the map task and begins reading the input file, passing one record at a time to the mapper callback. The output of the mapper consists of key value pairs. The reduce side of the computation is also partitioned. While the number of map tasks is determined by the number of input file blocks, the number of reduce tasks is configured by the job author. It can be different from the number of map tasks. To ensure that all key value pairs with the same key end up at the same reducer, the framework uses a hash of a key to determine which reduce task should receive a particular key value pair. See partitioning by hash of key on page 203. The key value pairs must be sorted, but the dataset is likely too large to be sorted with a conventional sorting algorithm on a single machine. Instead, the sorting is performed in stages. First, each map task partitions its output by reducer, based on the hash of the key. Each of these partitions is written to a sorted file on the mapper's local disk, using a technique similar to what we discussed in SS tables and LSM trees on page 76. Whenever a mapper finishes reading its input file and writing its sorted output files, the MapReduce scheduler notifies the reducers that they can start fetching the output files from that mapper. The reducers connect to each of the mappers and download the files of sorted key value pairs for their partition. The process of partitioning by reducer, sorting, and copying data partitions from mappers to reducers is known as the shuffle, a confusing term. Unlike shuffling a deck of cards, there is no randomness in MapReduce. The reduce task takes the files from the mappers and merges them together, preserving the sort order. Thus, if different mappers produced records with the same key, they will be adjacent in the merged reducer input. The reducer is called with a key and an iterator that incrementally scans over all records with the same key, which may in some cases not all fit in memory. The reducer can use arbitrary logic to process these records and can generate any number of output records. These output records are written to a file on the distributed file system, usually one copy on the local disk of the machine running the reducer, with replicas on other machines. The range of problems you can solve with a single MapReduce job is limited. Referring back to the log analysis example, a single MapReduce job could determine the number of page views per URL, but not the most popular URLs, since that requires a second round of sorting. Thus, it is very common for MapReduce jobs to be chained together into workflows such that the output of one job becomes the input to the next job. The Hadoop MapReduce framework does not have any particular support for workflows, so this chaining is done implicitly by directory name. The first job must be configured to write its output to a designated directory in HDFS, and the second job must be configured to read that same directory name as its input. From the MapReduce framework's point of view, they are two independent jobs. Chained MapReduce jobs are therefore less like pipelines of Unix commands which pass the output of one process as input to another process directly, using only a small in-memory buffer, and more like a sequence of commands where each command's output is written to a temporary file, and the next command reads from the temporary file. This design has advantages and disadvantages, which we will discuss in Materialization of Intermediate State on page 419. A batch job's output is only considered valid when the job has completed successfully. MapReduce discards the partial output of a failed job. Therefore, one job in a workflow can only start when the prior jobs, that is, the jobs that produce its input directories, have completed successfully. To handle these dependencies between job v, the joins we talk about in this book are generally equijoins, the most common type of join, in which a record is associated with other records that have an identical value in a particular field, such as an ID. Some databases support more general types of joins, for example using a less than operator instead of an equality operator, but we do not have space to cover them here. Executions. Various workflow schedulers for Hadoop have been developed, including Woozy, Azkaban, Luigi, Airflow, and Pinball. These schedulers also have management features that are useful when maintaining a large collection of batch jobs. Workflows consisting of 50 to 100 MapReduce jobs are common when building recommendation systems, and in a large organization, many different teams may be running different jobs that read each other's output. Tool support is important for managing such complex data flows. Various higher-level tools for Hadoop, such as Pig, Hive, Cascading, Crunch, and Flume Java, also set up workflows of multiple MapReduce stages that are automatically wired together appropriately.